In this video, we'll talk about the periodic structures of crystals and Bragg's equation or Bragg's law. First, let's look at this sodium chloride crystal. The smaller spheres are sodium plus ions. The green larger spheres are chlorine minus negative ions. Chlorine minus is bigger only because it has one additional electron than the neutral chlorine atom, and that creates additional electron repulsion. And because of this repulsion, electrons tend to stay a little bit further away from the nucleus so that they can stay away from each other. Sodium plus is smaller than the neutral sodium atom, again because sodium plus has one less electron and therefore less repulsion between the electrons. And let's look at some periodic repeating units. For example, if we look at this square, on the four corners you have four purple spheres. They are sodium ions. On the edges there are four chlorine minus. In the center there's another sodium plus here. So let's look at this square and then let's shift a little bit to this square. You observe the same square. Four sodium plus ions on the four corners and four green larger spheres. Those are chlorine minus on the edges. How about this one? Same thing. And also, if you look at the other direction, again, this square has four sodium plus ions on the corners and the four chlorine minus on the edges. So that's the periodic structure of the sodium chloride crystal. Now let's look at an unknown crystal. It contains only one type of particles, the red spheres, and I'm assuming it's very likely a neutral metallic atom, and this yellow bond then is a metallic bond. Alright, so and then we see repeated units. Let's look at this small cube that contains 8 atoms. 1, 2, 3, 4, 1, 2, 3, 4. And we can see this small cube is repeated in this direction, in this direction, and in this direction because we live in a three-dimensional universe. Now let's look at this famous Bragg's equation or Bragg's law. So there's a way to determine the distance between two adjacent atomic layers. How do we do that? Let's say this is the first atomic layer, this is the second atomic layer. The distance is d here. Let's get back to this picture. Look at this surface. Let's say this is the first layer of atoms. Many of those, 1, 2, 3, 4, 5, 6, 6 by 6, 36 spheres on top. That's the first layer. The second layer, of course, there are also 36 atoms. Now between the first layer and the second layer, there's a distance. We call that separation between the first atomic layer and the second atomic layer. So this distance, or this distance, this distance, this distance, denoted by d. How do we determine this d? Well, very simple. We just need X-ray. Let's say we have two beams of X-ray. So this is one beam, this is the second beam. Make sure that they are in phase at the beginning. So this is the starting line, this is the finishing line. So at the beginning they should be in phase. That means, well, they have constructive interference with each other. So these two waves add up. And also make sure when you detect these two beams, make sure you find a position at which these two waves also interfere with each other in the constructive manner. So when you see crest here, you see another crest here. When you see trough here, you see another trough here. Again, these two waves should add up at the finish line as well. But if you look at the distance the first beam travels and the distance the second beam travels, you can tell it's not fair. The second beam actually travels a longer distance. How much longer? This much. This short red segment plus this short thick red segment. Why? Because if you look at this line, it's equivalent to this line. And also this line is equivalent to this line. So really the second beam has traveled a longer distance. How much longer? This red thick segment plus this red segment. So what's the length of this segment? Very simple. If we have this distance d here, this red segment is simply d times sine theta. And this one is also d times sine theta. Why is that? Okay, let's say this X-ray forms an angle with the surface of the crystal, and the angle is theta. So this is theta. Okay, and the second ray, make sure the second ray is parallel to the first beam. Okay, these two beams of X-ray are parallel to each other. So if this is theta, then this is also theta. Okay, so this is also theta. And if this is theta, this angle is also theta. Why? Let me explain. Make sure that you draw a line here, and this line is perpendicular to the second beam of light. So this line and this line are perpendicular. So these two are perpendicular, and these two are perpendicular. And these two lines form a theta angle. Therefore, this forms a theta angle. So that's one type of analysis. Another kind of analysis is this. This is theta, right? This is theta, equivalent to this. This is theta, therefore this is theta. If this is theta, then this angle is 90 minus theta, 90 degrees minus theta. And this one, make sure this is 90. So you have 90 minus theta, therefore this angle is definitely theta. All right, because the three angles, when you add them up in a triangle, this one plus this one plus this one is 180. You have 90 here, okay? You just make sure you draw a vertical line here, perpendicular line here, that's 90. And this one is 90 minus theta. Therefore, this angle has to be theta. And then trigonometric function sine theta times this d will give you this red segment, this short one. Short and thick red segment has a length of d sine theta. Okay, what about this one, d cosine theta? But we don't care about this one. So d sine theta. This one is also d sine theta. Therefore, the second beam has traveled a little bit longer distance. How much longer? 2d sine theta. Okay, 2d sine theta. However, for the second beam and the first beam to be in phase, after this so-called diffraction, this is diffraction, the second beam has to travel either one wavelength or two wavelengths or three wavelengths, anyway, an integer multiple of wavelengths longer than the first beam. All right, so that means this d sine theta plus this d sine theta, therefore 2d sine theta, has to be 1 lambda. Okay, this is one whole lambda here, 1 lambda, or 2 lambdas, 3 lambdas, or 4 lambdas, longer than the first beam, so that these two beams are still in phase after this diffraction. All right, so before diffraction, they are in phase, in phase, in phase. And then after diffraction, they are still in phase only if the second beam has traveled an integer multiple of wavelengths longer than the first beam. So therefore, we have this famous Bragg's equation, 2d times sine theta equals n lambda. N is an integer, n can be 1, 2, 3, 4. So again, I drew this diagram here. Again, we have two beams of X-ray. This is our start line. This is our finish line. Again, the distance between the first layer, this is my first layer, my second layer, the distance is d here. So this is theta, this is theta. Therefore, this is 90 minus theta, and this one is theta. D times sine theta is equal to the length of this short purple segment. Same here, this one is d sine theta, so this is labeled with d sine theta here. Again, this thick purple line is d. This thinner purple line is d sine theta. Again, the second beam has traveled a longer distance than the first beam. The first beam is like this. The second beam is like this, and this segment, this arrow, has the same length as this red arrow. This arrow has the same length as this red arrow. So again, the second beam has traveled a longer distance of 2d sine theta. Again, this is 1d sine theta. This is the second d sine theta. So 2d sine theta. So make sure you understand, when you have a triangle here with this 90 degrees, this segment is simply d times sine theta. All right, so we're going to use this equation to compute the distance between two layers of atoms in a crystal. First, practice problem. An X-ray beam with a wavelength of 71 picometer PM. Picometer is 10 to the power of negative 12 meter. Is incident on a atomic crystal, and then the maximum reflection occurs at an angle of 40 degrees. So what does this mean? Maximum reflection. Actually, this means the beams are interfering with each other, and that interference is 100% constructive. That means in phase. So all those beams after diffraction are still in phase. Therefore, we know that this 2d sine theta has to be lambda, 2 lambda, 3 lambda, or any other integer multiple of lambda. All right, but just for simplicity, let's assume n is just 1. All right, and then we can calculate the separation between two layers. The Bragg's equation is n lambda times 2 equals 2d sine theta. We assume n is 1, therefore lambda is 2d sine theta. And d is simply lambda over 2 sine theta. Okay? We plug in numbers. Lambda is 71 picometer. Again, 1 picometer is 10 to the power of negative 12 meter, or 0.01 angstrom, or 0.001 nanometer. All right? So again, pay attention to the units. 2 sine theta, 2 times sine 40 degrees. I'm too lazy to even use a calculator, so I used this Wolfram Alpha website. If you do Control-click, you will see what I did here. I typed 71 divided by 2 times sine 40 degrees. Make sure you use this left and right parentheses. Here, this is to ensure this 2 and this sine 40 degrees both appear on the bottom. Okay, so 71 over 2 sine 40 degrees. The result is 55. This 71 is in picometer, therefore 55 is in picometer. So I got the answer here, 55 picometers. Done. All right, now let's look at practice problem 2. Well, an X-ray beam with a wavelength of 5.00 picometer is incident on a atomic crystal. The separation between two layers is 50 picometers at what incident angles? This time I ask you to compute the angles with the maximum reflection be observed. There can be many angles because this integer multiple of wavelengths, this integer n, can be 1, 2, 3, 4. But let's just calculate the two smallest angles. All right? Okay, so you can pause here and work on this practice problem before I show you the answer. Now the answer. Bragg's equation. Again, n lambda equals 2d sine theta. So sine theta is simply n lambda over 2d. In this case, let's say, let's work on the two smallest angles, therefore two smallest sine thetas. So we're going to use n equals 1 and n equals 2. All right? So when n equals 1, we have lambda over 2d. When n equals 2, we have 2 lambda over 2d. The answer is very simple. Lambda is just 5 picometers. D is 50 picometers. 5 over 2 times 50, we got 0.05. There's no unit here. The units cancel. The second angle, 2 lambda over 2d, is simply lambda over d. Lambda is 5, d is 50, so 0.1. All right, so why did I bother to give 5.00 and 50.0? I just want to ensure that you understand the importance of significant figures in science. So we have three sig figures, the result should contain three figures. Therefore, sine theta is 0.0500 and 0.100 when this integer is 1 and 2 respectively. And then if sine theta is 0.05, the angle is 2.87 degrees. If sine theta is 0.1, the angle is 5.74 degrees. Again, I'm too lazy to use a calculator, so what I did is this. So you can simply use Wolfram alpha, just type arc sine 0.05. It's going to tell you it's 2.866 degrees. This number is in radian, so you can say 0.05 radian. All right, but my question, well, you can answer this one or this one. Both are correct, but if you say 2.87, you have to say 2.87 degrees. And if you say 0.0500, you have to say 0.500 radian. And I think there's another way to do it. I'm going to just say sine theta or sine x. Okay, it's very hard to type theta, so I'm going to just do this. Sine x equals 0.05. And then give me the answer. Okay, here's the answer. All right. What? Okay, it didn't give me the answer, so let's get back to arcsine. Arcsine. This time I'm going to show you arcsine 0.1 because we need this number as well. So arcsine 0.1 is 5.74 degrees. 5.74. Again, I encourage you to use Wolfram alpha to do all these calculations.